So hi everyone. Last time we discussed the birth process, the process by which we can add new members to a group, and we said that the rate of addition could be some birth rate, lambda b. And then we discussed the slightly more complicated death process. In this particular case where we start off with a certain number of members, and then our rate is proportional to the number of existing members, kind of watching the population decay. So now we're going to do the birth-death process. And the birth-death process is going to be interesting because at this point it's not clear at any given jump time whether you're adding a new member or removing a member from the group. So at this point the elements of the pi matrix are going to be, or the transition probability matrix, are going to be interesting to learn. So let's go ahead and talk about the birth-death process. Here again, we will have a constitutive state space of sigma m, which is going to be equal to m minus 1. I will have a S1, my initial states, which are going to be sampled from a categorical. And, with some probability rho. Now again, I may have a fixed number of initial members. Maybe I start off with 100 initial members and so forth. But I think what's the most interesting for this example here will be the transition rule. Categorical, 0, 1, 2, with some matrix pi, Sn, which we'll turn to in just a second, and finally Hn conditioned on Sn, which will be sampled from an exponential distribution, which will depend on lambda Sn, just like we had it for the death rate. And I should have written the conditioned on Sn earlier a little bit more explicitly, the small Sn. But either way now, this rate is going to be a little different than the pure death process, and this pi will also be a little different. So let's go ahead and talk about the form for the rate and talk about the form for the pi. So the pi matrix will look something a little bit like this. Again, we have 0 along the diagonal because that's the paradigm in which we're operating. Now we're going to have some probability P0 of adding a new member, and the probability of adding 2 members is 0. Probability of adding 3 members is 0. So the rest of these are all zeros. But you also have some probability of going from 0 members to 1 member. So we're going to have a Q0, which in some sense is going to be the probability of death. And, we cannot go from 0 to 2. We cannot lose 2 members at once. That would involve 2 jump times. So the rest of these elements are all 0 as well. If we start off from state 1, we have some probability of adding a new member, and we're going to call that P1. And then if we start off with state 1, we cannot add 3, or we cannot end up with 3 members. Again, that would involve 2 jumps, so the rest of these elements are 0. And similarly, if we start off with 2, I can do it like this to make it a little bit neater to make sure we know what I'm filling out here. If I start off with 2, I can also go down to 1 member. I'm going to call that Q1. Now, one thing immediately that's important to point out is that my probability of adding a member or the probability of removing a member, if I'm starting off from state 0, is equal to 1. That's equivalent to saying something, either I add a member or I remove a member, but those are my only 2 options. Right? Furthermore, P1 plus Q1 must be equal to 1. Now you're going to say, well, one second, this is not the same as saying that the elements of a row must sum to 1. That's also true. It's also true that all of the elements of any individual row must sum to 1. In general. So this and this are properties of the birth-death process, implying that only one of two things can happen when I have a jump. And this is properties of sort of conservation of probabilities. So just looking at the sort of these two relations here, if P0 plus Q0 is equal to 1 and P0 is equal to 1, then that sort of implies that Q0 must be equal to 0. In some sense, that's kind of obvious. If I start off with 0 members, no one can die. All I can do is add a member. So therefore, the probability of going to the next state is actually 1. There's nothing to learn, because I know that going from 0, I must go to 1. Well, now, when I have 1 member, things are a little bit more complicated, because at this point, yes, 1 member can decay, or 1 member can be added. So at this point, the relationship is not so clear anymore. Q1 is not equal to 0, for example, because I have some probability of removing a member. Okay, so let's write out what the Q's and the P's are. It's going to be the very same as the mathematics for the death process, and the details of the mathematics are contained in the appendix. But if you believe me that the birth process is occurring in such a way that it is independent of the population, just with some rate lambda b, and that the decay is proportional to the number of members, then we find that PS, so that's the probability when you're in the nth state of adding a new member, is going to be equal to lambda b divided by S lambda d plus lambda b. And similarly, QS is going to be equal to S lambda d divided by S lambda d plus lambda b. And finally, when we write something like this down, that the holding time conditioned on the state that I'm in depends on lambda s, we will find that lambda Sn is equal to Sn lambda d plus lambda b. Now, we can easily verify in this case that PS plus QS is always equal to 1 in this case. So when I transition out of my state S, I either add a new member or I remove a new member with some probability 1. And the probability of addition is this, the probability of subtraction is this. In some sense, it's a little bit intuitive, because the probability of removing members is proportional to however many members I have, and the rate of removal of each one of these independently. And the probability of addition of a member must be proportional to the rate of production. So if I consider these two and this constraint, I can sort of intuit that these must be the form for PS and QS. Though again, the careful derivations themselves are in the appendix. And the derivations themselves follow from the following property, that if I have multiple competing events, in order to be able to find sort of which of the events comes first, I find that the event that comes first is proportional to the rate, or so the rate of the event that comes first is proportional to the sum of all of my competing events. So the competing events are birth and death for however many members that I have. Again, this is a result that's derived carefully in Appendix D, if you care to sort of follow that derivation. Otherwise, you can sort of look at the simulation, get an intuition for it. And by the time I've derived this lambda Sn, then I can derive the PS and the QS if I choose to. So think of it this way. Suppose that I have, multiple different members in a group. And I think about what happens at the next jump time. I have two options. Either I can add a member, or I can remove a member. And removing a member is going to be proportional to however many members I have, and the addition of members is going to be proportional to the rate of birth. And if I want to be super specific, QS is going to be proportional to not only Sn, but also the death rate. And that's going to tell me which one of these two options I select. So let's look at kind of what a typical time series for birth-death process may look like. These would be my constitutive states. If I start off with 0 members, then I cannot remove from 0, so only birth can happen. So I'm going to add, at least for my first state, I'm going to add some member, and the waiting time is going to be drawn, or this sort of holding time is going to be drawn from the exponential distribution with some rate lambda b. Then, one of two things can happen. I can either lose a member or add a new member. But suppose, for example, that my rate of birth, lambda b, is much, much larger than lambda d. Then what's going to happen is that I'm going to keep adding new members, and deaths are going to happen occasionally, but it's going to be rare, and it's typically going to happen by the time the number of members in the group get higher, because now Sn multiplied by lambda d at one point becomes roughly of the same size as lambda b. So if I consider sort of some population, I'm going to start equilibrating at some point where I will be adding members and removing members in equal proportions if the birth rate, lambda b, is generally larger than lambda d. Now what happens if lambda d, I should say, is much, much larger than lambda b? That's going to be a slightly different scenario. Because at this point I may occasionally generate a new member, but it'll take time because the birth rate could be very slow. And as soon as I add a new member, then because lambda d is so large, it just decays right away. And then I have to wait again for a new member to develop or to be added to the group, and then it decays right away, and so forth. So this is where lambda d is much, much larger than lambda b. This is where lambda b in general is greater than lambda d. Not much greater, and it depends. And this equilibrium, sort of the population at which you stabilize, depends on both lambda b and lambda d. Now, let's talk about the case where you don't start off with 0 members. And in this particular case, if we run a simulation, and we'll look at it in the context of the simulations for Chapter 2, but I have some time, and I have constitutive states here. If I start off with some population, and I can say that lambda d in general is less than lambda b. But remember, if I'm starting off with a large population, what I really should be comparing is this to the birth rate. So if my population is 1,000, and maybe my death rate is 1 per second, and my birth is maybe, 2 per second, yes, 2 is greater than 1, but on the other hand, I'm multiplying by 1,000. So initially, I'm going to observe a lot of death events, and then eventually, birth and death will start equilibrating, and I will get to a steady state population once more. Right? So I will observe a steady state population following sort of an initial sort of drop in my population. And the steady state population will be, and we can calculate this, proportional to lambda b over lambda d. And in fact, there's an example sort of walking you through this. So, in the textbook. So with that said, this sort of concludes the slightly more complicated birth-death process. Now that we've finished sort of discrete states in continuous time, we will discuss the slightly easier paradigm, in a way, of discrete states in discrete time before turning to the continuous state-space paradigms. Thank you.